And at end, I will introduce some quantum real device applications in terms of Army or the US. Actually, we have some project from the US Army, so I will talk about a little bit from that and some quantum-based optoelectronic devices at the end. So you can see here some recent progress, how the field is moving. So if we see, this is basically the integration of two-dimensional materials with the existing CMOS devices, which is based on silicon oxide. So whatever computer, if you see here, this computer, this is based on the silicon or silicon oxide devices mostly. So there is a lot of billions or trillions of transistors based on silicon, but people still trying to improve this performance of these devices. So this is one of the integration of 2D with the CMOS devices to go beyond this silicon technology. So this is actually the projection that people are thinking that this field can move towards this direction. So this field actually predicted in 2022. It's a very recent field that people are moving forward. So there's a huge applications or huge field for research, extensive research and high quality research in the past, I believe that in decades. So here basically we are not moving all of them. We are really focused on quantum technology in terms of materials and field device applications. So you might ask me what is 2D, right? Many of us you don't know, many of us know, or many of us don't know. So basically these two guys from University of Manchester discovered the graphene, which is a single atom carbon layer. And because of this discovery, they got the Nobel Prize in 2010 in physics. So how you consider this two-dimensionality? You know the human hair, right? If you know it's a very tiny, thickness is less a few micron. If you make it 1,000, if you divide this 1,000 times, if you cut it 1,000 times, so if one single piece thickness is basically the thickness of this single layer. This is close to 1 nanometer or less than 2 nanometers. So it has a very beautiful, interesting material in terms of physics. Why is that? Because it has a tunable electronics, optical and optoelectronic properties. So this was first discovered, but this material was semi-metal. It's not the semiconductor. If you talk about the semiconductor devices, even the semiconductor material, you should have certain band gap. But if you talk about the semi-metal or metal, it has the conduction band and valence band touch each other, and that is not useful for certain semiconductor device applications. So after discovery of this material, people look at different kind of two-dimensional materials, especially the transition metal dichalcogenides. So some you can see some structures how it looks like. Its chemical formula basically MX2. So this metal is basically sandwiched between these two chalcogens. You can consider here this yellow is a chalcogen and this gray one is the metal. So this metal is basically sandwiched between these two atoms of the chalcogen. So this material has intensive research in optoelectronics application for semiconductor devices. So I already told you why it's important. So this material has very high carrier mobility. If you consider single layer, it has very high carrier mobility, tunable band gap, and light absorption cross section is very high for various applications, and it has a thickness dependent high reach of electronic properties. So before I go to the main topic of this today's talk, I just introduce the hetero interface. So if we see any electronic devices, the hetero interface is very important. Like if you consider any electronic devices, it has electrodes and it has some functional material in between these two. So the interface between metal or semiconductor, many of the students may have already studied these things like metal semiconductor junction, semiconductor metal junction, metal semiconductor or semiconductor junction. So this interface basically played a crucial role in different kind of device application like type 1, type 2 or type 3. Each and every material interface has the different applications. So my main focus was initially like the interface physics, how these excitons or charge carrier transport from one side to other side. So in terms of LEDs, solar cells and tunneling field effect transistor applications. Not only the application, also the fundamental physics in terms of like the time scale, how it moves from one side to the other side. So I will just give you small part of my PhD work. So basically I worked on these heterostructures of 2D, 0D, 2D, two-dimensional material, one-dimensional interface, and 2D and 3D interface of this kind of study. So you may ask me why it's important. Just for an example, if you see the solar cells has basically, in case of organic solar cell, it has two different kind of materials. So why is that? So when sunlight from here in this active layer, one material absorbs the sunlight, So when the sunlight falls in semiconductor, so you can generate or create a pair of excitons. So it's bounded by the electrostatic positive and negative charge, bounded by the electrostatic force. And somehow you have to break these excitons at the interface, and you should collect these electrons and holes at opposite electrons. And then this photogenerated charge carrier you can use. So it's very much important how much time it will take to generate this exciton, and how much time it will take to dissociate, that means separate, and how much time it can travel from the active layer to these two electrodes. So otherwise you might lose these excitons and you might not get the free charge carrier at the two different electrodes. So yeah, in this case, my main goal of this work was to introduce these TMDs in this organic semiconductor system. As I mentioned before, that organic semiconductor has very low charge carrier mobility. So I tried to understand the exciton phenomena at the interface between these two materials. Not only that, how you can improve the charge carrier time scale, and also the electronic charge carrier collection for enhance the efficiency of this kind of devices. So another reason is that, as I mentioned before, this is a highly absorbing material. Cross sectional is so super high. So if you look at the different materials, especially the thin layer of this transition metal dichalcogenide, that can absorb 10 times higher sunlight than the existing silicon oxide. So that was another motivation of this kind of work in the last few years for my PhD research. So yeah, another key research that I just want to highlight from my PhD time. So it's a multiple exciton generation. So why is multiple exciton generation? If we consider, like, you have a single photon. If you think about the physics, not the materials, you have a single photon and you have the semiconductor. Basically, you can create, with a single photon, you can create only single exciton. If you generate a single exciton, so you have only single electron and holes, right? So Shockley and Quizat, they theoretically started that if we have the single photon and if we can generate a single exciton, then only we can reach 33.7% power conversion efficiency of the sunlight. So last 10 years, people have different approaches how we can let's say exit this limit. So there are various theory how to improve that. One of the most important parameter or important way is that if you can excite a single photon and you can generate the multiple exciton, or one or more than exciton in your system, semiconductor system, possibly you can generate more exciton, more free charge carrier, and that can lead to exit this limit. But this is not easy things. But because if you consider the silicon if you consider silicon a conduction band and valence band, the material is the band structure is continuous. So if this is possible only when you have quantum dots. Quantum dots is fall in the quantum design. We call this quantum material, right? It has a discrete energy level in the conduction band as well as the valence band. So if you can excite this material twice energy than the band gap, you can generate more than 2 excitons in this system. But you need a specific site to dissociate the charge carrier and also the collection. So we were very lucky to, let's say, do this work to generate multiple exciton in this quantum system with this 2-dimensional material. Basically, this 2-dimensional is here we use the 2D molybdenum disulfide as a site to accept the charge, multiple exciton generated charge carriers, and we are able to show this fundamental physics, how much time it takes to lead this charge carrier generation as well as the extraction of this multiple exciton, and we showed that it is possible to exit 33.7% power conversion efficiency in the system. So this was a highlighted paper in my PhD time. So this was published in ACS Energy Letters that time. It's a high impact journal. So yeah, now I will come to the main work that I want to discuss today. So this is a very emerging 2-dimensional monochalcogen materials and heterojunctions with different kind of 2D and the fundamental physics. So as I discussed before, this TMDs is basically the monochalcogen. One metal is sandwiched between the 2 chalcogens, but this monochalcogen is a little bit different. You can see here, this is actually the corrugated T structures, but it has 2 different elements. You can see this green one basically the chalcogen, and M is the metal, and metal is basically grooveful metal, is tin or germanium or selenite, telluride. So this is the top view. What is this importance of this material? If you see the structure, this materials and this material, this is the isotropy material, but this has these anisotropic structures. if you consider like Amstel and zigzag direction, it has two different band gap and two different direction that create a new high risk physics for optical refractive index of two different direction, and also the transport of electron transport in two different direction is very different. And also it has a very specific symmetry of the crystal that I will come in the later slides. So it has a very low crystal symmetry, and crystal symmetry is very important in fundamental physics in terms of optical and electronic properties. So that is this piece is very critical for these materials, and also this material is quite stable, as mentioned in the inauguration time, professors, that the stability or environmental acceptance of the materials is very important for real application. So this materials is quite stable. So here I basically talk about the low crystal symmetry and the high carrier mobility, and also the absorption coefficient or the absorbance of these materials in the next slide. But as I mentioned, you need the monolayer or the single layer of this material. So that is very important to produce this material as a single layer. Then otherwise you cannot get the important optical or electronic properties or electronic properties. So if you look at here, the interlayer binding energy, which is a critical parameter to produce this kind of material as a single layer. So if we consider the graphene, you see the interlayer binding is very low KBs, but in metal monochalcogens, the interlayer binding is very high. So it's very hard to produce this material as a single layer. So our main focus first was how to produce this thin layer of this material. So you can see here the status when we started this work. Very few work has done. First started in 2015. This Manchester group, O'Brien, they have shown few layers of this material, but there was nothing studied for optoelectronics or physical properties or any physics of this material. They just introduced this material, and which was published in JACS 2015. So, sorry. Then I have a intensive review of this field in terms of next generation electronics and optoelectronic application, which was published in 2020 in Advanced Science. Then our main focus was how we can create this single layer of this thin sulfide, which is very important materials for that. So there are various methods or various techniques have been used in past few years, not only this material, the other materials or two-dimensional materials. So this is basically mechanical exfoliation, maybe many of us knows. So this is Costin method. This was the technique used to produce graphene and got the Nobel Prize. Very simple method, just Costin. If you have 2D crystal, just do multiple times like peel off, and you can create a single layer that is a few nanometer thin shape, like few hundred of microns and later dimension. So then this physical vapor deposition, this is an industrial method basically used for various applications, technological applications, and then the very easiest way is the liquid phase exfoliation for flexible electronics or optoelectronic applications. So here basically we focus two methods for our materials role. We use physical vapor deposition, basically the chemical vapor deposition and liquid phase exfoliation. So here initially I will talk about the liquid phase exfoliation techniques, and then some part I will talk about the physical vapor deposition. So as I mentioned, we have the main target was to produce this material. So here is the schematic of the liquid phase exfoliation. So this is a very simple but very critical because we use some liquid to exfoliate this 2D material. So just a short introduction. The bulk crystal of this 2D the material we pour in a solvent, and we use the ultrasonication sound to create some forces. You can see here basically the whole schematic. So when you will produce this ultrasonic sound, it can create some bubbles. That bubbles actually explode, explosion happen, and they create some forces in lateral and vertical direction, and that makes like a thin layer of this material. So here is some schematic. I will not go in detail. So yeah, so we applied this technique to produce thin layer. The first work was like this production of few layer, not the monolayer. So here you can see the Raman spectra, which is a very, let's say, important tool to understand the vibrational properties. Not only that, the layer number, presence in any kind of two-dimensional material. So our intention was to understand the optical properties. So we employed the Raman spectroscopy to understand the thermal properties in the system. So it has many different vibrational modes, which are inactive or active. It depends on the modes and the laser excited source as well. So in this case, we have 4 vibrational mode appear in this case, and we started the temperature dependent Raman spectra to understand the thermal properties. Not only that, first for the temperature coefficient, That is the phonon energy and phonon lifetime in this case. So you might know, if you study the solid state physics, if we consider it solid crystal, so we consider two atoms is bounded by a spin, right? And this energy is basically mediated by the phonons from one side to the other side. So that phonon energy, basically you can see this peak shift, and this cool with the half exit will give you the phonon energy. If you consider the exciton, it has certain energy, certain lifetime. It can stay in the excited state, right? So, and it can fall in the ground state or the valence band of the semiconductor. So similarly, you can consider, like, here is the vibration of this material from one atom side to other atomic side. So here you can see some the sheets is very small in size, is around 1.2 nanometer thickness, and the lateral dimension was few micron. So here how this phonon energy basically shifting from with temperature. So we studied basically the first order temperature coefficient here, and also the phonon lifetime. So you can see how this phonon lifetime is changing with the temperature. I will not go in detail hardcore physics here. We reported in the last time. But important things here I just want to show you is, like, if you consider the other two-dimensional materials, especially for graphene, MOS2, or other two-dimensional materials, if you see here, the thermal, this is basically the temperature coefficient is very high, which is very important for, let's say, thermoelectric application, where this thermal energy converted to the electricity. So not only that, we have also focused on nonlinear optics. I am not showing here, that is J-scan, and we have also find a very high saturation absorption coefficient in this QDR system. So which was actually published in Nature in 2020. Okay, then we focused on the isolation, as I mentioned, right, the monolayer, which is very critical to understand the physics or application point of view. So here our main motive was to produce the thin layer, which is monolayer. So here, after studying the previous work, we realized that this is very highly sensitive to temperature, right? We might introduce some temperature in this crystal that can relax vertically. And if we employ some energy, that is the sound energy, that is ultrasonic sound energy that can help to buy the part of the system, and we can get very thin layer. Yeah, and it's what actually. So here you can see we use 25 degrees centigrade and 50 degrees centigrade temperature during our material processing, and we are able to produce very thin layer. Sorry, some of the images are missing. So here you can see, as I said, it's Amsterdam. It has a high anisotropic material. This is a high resolution atomic force microscopic image. Here you can see that clearly you can see the crystal bends, the artificial and zigzag directions in a single layer of this steel sulfide. I'm sorry, some images are missing here. Here we have confirmed the chemical compositions, and we have some Raman spectroscopy of the system, which are missing here, and the UPS ultraviolet photon emission spectroscopy that have been used to understand this system. So this is not our main topic, because we want to study some fundamental physics as well as the electronic application. As I mentioned in the first slide, that this had a high absorption coefficient. So this is very good for this photo detection part. So here what we did, we employed this material for field effect canister as well as the photo detector. Here you can see the single layer field effect canister. And here you see the EB lithographic devices, some of scanning electron microscope image. We studied first the transport behavior of the single layer of in sulfide. You can see here we have different region has different transport properties. So we have this ohmic region, then gap field limited space charge conduction, and space charge limited conduction region in the system. So now we introduce we illuminate few different colors of laser. Here you can see 254 nanometer, 405, and 405 nanometer, 254 nanometer laser. In the dark, we don't have any response. We have shining this laser. We have this huge change in the current in the system, which is zero under zero bias in the system. So now we individually employ these lasers as well as the bias system, and you can see clearly how it responds. So our motive was to use these lasers to understand the photo detection properties in the system, and not only that, we have studied the interface physics in the system, what actually happening at the gold electrodes and this tin sulfide. So we realized that this charge transfer from this tin sulfide, single layer tin sulfide to this of these two electrodes in the system. I'll not go in detail. So here we basically find out the response time and the decay time of this system, which is pretty much good. I will come into the next slide in this system. So if you have a device, so it is very important the stability at environment. If it is not stable, you cannot use for the real practical applications. Before that, we did some real experiments. So we use a white light instead of these lasers, because if you want to use this device in the atmosphere anywhere, there is a white light, there is other lights, right, as well. So you should have the selective light detection. So you can see here, this is the dark condition. When we have this UV light, that is 254 nanometer, we have a certain price. So in this case, this is dark condition, okay? Then we have turned on the white light. It's air, it's a normal light. So still we have the same response. There is no change in the response in the presence of white light. So this is pretty good for this kind of device for real applications. And we also observe that it's quite stable. If you see here, this is the first day, the blue one, and after 60 days, you can see the current is little reduced. And it's we keep this device in the normal atmosphere. So it's quite stable, and performance is pretty good for long-term applications that we believe. So this here you can see some comparative studies of different 2D materials that have been recently reported, and we have a pretty good response time as well as the responsiveness of the system. So which was recently been published in Advanced Science last year. How much time? Almost 15. Okay. So yeah, now we're working on large-scale application, large-scale electronic applications. So some of our students are working this project. So we are able to produce like a large area thin film for large electronic applications. So we are working on this field. Why, you may ask me? So we are moving for not only optoelectronic applications, some biomedical electronic applications that we're looking for, especially the bioelectric sensor or the monitoring some patients' activities. So this project is undergoing, so I am not going detail about that. So as I mentioned in the anisotropic of this material, maybe I should go in the next slide. So anisotropic material, there's a various way how to prove that these materials have optical or electronic anisotropy. So one of the important tools is anisotropy Raman spectroscopy or absorption or photoemission spectroscopy. But one problem here is the flex size is very low, and for optical system we have a certain optical limitation. So because most of the laser beam is more than 500 nanometers or close to 1 micrometer spot beam. So if you focus with this 1 micrometer spot beam and your material is lower than that, and the material is oriented in different direction, basically you will collect the signal from all the differently oriented samples, and it's quite hard to understand the anisotropy or the crystal orientation dependent optical properties. So in this case, we use a microscopic techniques which is developed in the center. So this is polarized second harmonic generation. What we did here actually, we scanned a certain domain of the sample where multiple flakes situated in different directions. What we did actually, we just collect the second harmonic signal, and from point by point we try to get the signal, second harmonic signal from each of the flakes. Here you can see 1, 2, 3, and 4, and you can see here how these lobes are changing in 3 or 4 different flakes. So this is basically signifying that your flakes are differently oriented and which are basically anisotropic in nature. So later we studied in detail about this material for second harmonic generation and also the third harmonic generation, which I'm not going to go in detail. So this one was published in last year in Advanced Optical Materials, and fortunately we got the inside cover page of this work. So now I will just give you about a very short introduction about the quantum dots. So we all know about the bulk materials, right, 2D materials. But quantum dot is a little bit different. You see here this 2D. If you move to 3D to 2D, and 2D to 1D, 1D to 0D, you see how this energy states are changing over dimensionality. So I think you might know these things, but if you go to zero dimension, you will have the discrete energy level at the conduction band or valency band of the system. So this is very quite interesting for study in fundamental physics. Not only that, of the electronic application, as I mentioned in this multiple exciton generation. So that is one of the important applications. Not only that, people now trying to explore some other applications as well, like the emissive laser applications and other applications. So here main motive was to introduce like quantum dots in this system, and our main target was how we can visualize this directional dependent these optical properties. So if, as I mentioned, that the structure of this materials is corrugated tin, like you know, all the tins is like a wavy structures, right? And it has two different directions and two band. So here basically we explored like the directional dependent PL emissive properties of this system. So we use various spectroscopic techniques to understand the optical emissive properties. So I will not go all of them. So what I would say here we observe two different emissive sites. One is 2.76 electron volt, 04 electron volt, which is basically the band in the armchair and zigzag directions that I mentioned before. And we basically support these things with time scale, different time scale with the different laser techniques. And we try to understand what is time scale for these electrons to comes from the excited state to the ground state of this quantum system, which was published in last 2021 in Applied Physics Letters, basically for the quantum applications that we talk about. And yeah, this might be, I can skip for now. This is another 0-2D heterostructures, so it's based on molybdenum disulfide. And here our motive was that this MOS2 has two bands, basically. The valence band has a splitting. So if we consider two bands, A and B exciton, here you see A and B exciton. So always this B exciton emission is suppressed because of this A dominating B exciton, A exciton. So here main aim was, if we can switch with electronic bias, basically this can be used for emissive, two different colors. So how do we do that? There's a various technique, various method recently been used, but this is very expensive because you have to do, this is basically the nanoperiod, and you have to do some lithography techniques before you do or fabricate your device. So we thought in a different way. We introduced a different glass phosphate, which is a transparent semiconducting material, which is well studied. So what we did actually, we introduced this 2D inside this glass matrix, and this glass matrix has some nanoparticles, and it's a plastic nanoparticle, and plasmonic nanoparticle has a surface plasma, which is a positive and negative surface charge. This actually, this plasmonic band actually can resonate with this B exciton. When it's resonant with this B exciton, you can tune this B exciton emission, basically, and you can dominate this one. So we basically here we studied the fundamental science. You can see here this A exciton is basically diminished, right? If you look at here, yeah, A exciton is basically the dominating one, but B exciton is not. So in this case, we basically studied how you can tune this B exciton in the presence of this glass phosphate, and we are able to understand the dipole-dipole interaction. Basically, it's a plasmon and exciton coupling in this system, which is basically responsible for this excitonic enhancement, emissive enhancement of this B exciton in the system. So here you can see the schematic how it works basically. And good thing in this case, this material is useful for the flexible or transparent display applications. That was the main. This was the one European research sponsored project basically. So this one was published in scientific reports in Nature Journal last year, not last year, 2021. So now I will basically come to the real two-dimensional quantum materials or the quantum technology that I have been studying in the last 1.5 years working on. So before I go to the two-dimensional quantum materials, I just want to give you the timeline. So there's a lot of work in bulk magnetic material last decades. For if you remember, before let's say 2010, we have this CD compact disc. Before that, we have the floppy, and it's made of mostly the magnetic material, and it's a bulk material. Then the technology is moving towards the small size. Now you have a chip, right? It's like a tiny chip, like 1 terabyte storage. Is because of the material development, functional material or quantum or magnetic material. So there's a lot of study of the bulk material, then people realize why not this two-dimensional material, because it's a very thin layer. It's a 1 nanometer. If it's 1 nanometer, and if you can keep like 1,000 terabyte of data, why not? Not only that, the people also the field is also moving based on the spin, right? It's not on the charge. So thin two-dimensional material is one of the important, because is 2D materials. What is 2D materials? Basically, you are talking about the two-dimensional system. So basically, you are suppressing one dimension of the excited movement. When you will suppress the one dimension, you have a more flexibility, tunability in your system, even as electrons and holes. So you can play more beautifully the electrons, the spin or spin up or spin down in the system. So there's a lot of research in the last couple of years, starting from 2016, and there is a lot of different materials have been developed. In most recently, this chromium triiodide, one of the most important magnetic materials or quantum materials, has developed. But problem with these materials are quite unstable. When it comes to the air environment, it is immediately degraded. So then people looked at different two-dimensional materials. Not only that, the QE temperature. If it is a magnetic material, it has QE temperature, right? If it is low temperature, that is not useful for the real application. There's a lot of people focused how you can increase this QE temperature for real applications. So our first, the main two target was like stability and the magnetic properties of these EMDs in terms of QE temperature rising at room temperature, I would say. So this is the first paper from our group that we are able to introduce this MOS2 as a magnetic room temperature ferromagnetic material. So this materials was basically developed in the center. So we use this chemical vapor deposition technique. This is in situ process that have been developed and published in Nature Com last 2020. And here you can see some characterization of this material. So this is a flex two-dimensional materials, molybdenum disulfide, scanning electron microscope image, and this is the structure. What we did basically here, we replaced some molybdenum with iron in the iron side, and here you can see the high resolution microscopic image. This side is basically the iron, and this side is the molybdenum. So here we started some other techniques just to confirm about the material's properties. So I am not interested to those things, and yeah. So I must talk about this one, because I said, right, the room temperature is most important to utilize this material for quantum technology or quantum device or any device application. So here you can see the image hysteresis loop. That is one of the important characteristics to confirm about this material. So here you can see these two windows. So the blue one basically at 300 Kelvin and 5K, red one is 5 Kelvin. We see the hysteresis loop at room temperature as well. That is one of the huge breakthrough in the field for the real, next generation electronic and electronic applications, especially in the quantum design. So this after that we have this published paper, we basically focus on the large area growth of this to be, because we are thinking about the large scale electronic and optoelectronic applications. Some project is with some company that are funding for this project. So yeah. Right now, we are working on some applications in this with this material. So magnetic tunneling junction for the storage application, and some energy applications, especially the energy conversion, is based on quantum design. So before that, one important thing is the spin phonon coupling, which is very important in two-dimensional magnetic material. Whenever we talk about the spin, is a magnetic material. So how the spin is, let's say, interact with these magnets, that will impact not only on the device performance, also the fundamental understanding in this system. So our first motive was to understand spin phonon coupling and the strength of the spin phonon coupling, how the spins of the electrons is coupling with the magnets in this system, because the ferromagnetic material is in domain. When you apply the magnetic field, this magnetic domain will be aligned in a particular direction. Now you have the spin in this system of the electrons of holes, how these are interacting and how you can understand how you can convert the energy or the storage state. So this is some development in the lab that I did. So we don't have optoelectronic. This is a capacitor. Basically, you can go 4 Kelvin temperature or 4.5 Kelvin temperature. So I developed this setup with the commercialized one. So this is developed by me. So we are using here a chip that can carry any kind of devices here, and we can cool down the system like 4.7 Kelvin totally automated like a software that we developed with in our lab, MATLAB, either MATLAB or Python that you can control. So you can employ some magnetic field here as well, and also the optics as well, like different kind of lasers that you can use in the system. So first we started this temperature dependent normal spectroscopy to understand phonon dynamics and magnetic phonon interactions, to understand the spin phonon coupling. So I will not go in detail here because of time probably. So here what we observe, here you can see this for dot 1, this magnetic phonometer. So there is change in the in the phase. So it's not clear here. So we try to understand with the Brunson model. Maybe you might know these things who are from the solid-state physics background. So we try to understand first the I, that is the first order temperature coefficient, with this Brunson model. So here you can see how this phase of these two slope is changing in two different, let's say, modes of vibration. When you talk about the 2D materials, it has two different vibrational modes. One is the vertical, the outer plane, one is the in-plane. So basically we understand how this in-plane and outer plane vibration mode changing over temperature. That is basically the phonon energy and phonon lifetime in this system. So here you can see two different the slope, which are very different than this normal MOS2. And we try to understand why this is happening here. This is basically the Curie temperature. As I said, like we already studied, the Curie temperature is close to room temperature. So we believe that this temperature is basically because of the phase change of this material and Curie temperature. So then we basically collaborate with this guy from the University of South California, and they are doing some theoretical study to understand this, and they find the same observation theoretically. And this paper, I must say what exactly they are doing. So as this is a quantum material, right? We consider a quantum system. We consider a quantum system. So if we talk about the quantum system, so we are talking about the spin Hamiltonian in the system. So just forget all the stuff. So when we consider this Hamiltonian, this Jij, that is basically the spin phonon coupling strength. So we are trying to understand what is the value of this spin phonon coupling in terms of the theoretical part and the experimental part that we observe in our system. So what we realize here that we have is directional dependent, like the in-plane and out-plane vibrational spin phonon coupling in this system. That's why you see here. That's why you see here two different slopes in these two different cases. So this is not published yet. So very soon we are going to communicate this paper. And we also studied some other techniques to understand this phenomena that we observe in the system. So I also collaborate with this Professor Dimitri Basu from University of Columbia in New York. So they did some magnetic force microscopy. So what we try to understand here, as it's a ferromagnetic material, it's a certain domain, right? So we are trying to understand how this field interact with this specific domain and how this domain is changing over temperature. So this is undergoing experiments. It's not finished yet. So yeah. Now I will basically talk about the last part of my talk. So spin-based optoelectronic devices. So most recently in 2017, people have started in spin photovoltaic instead of charge-based photovoltaic. So this paper came out in 2017 in Science. So what they have shown, this is actually spin out. They inject some spin from this magnetic material, this 2D carbon conjugated materials, and they try to implement, not only implement, I would say, try to convert some illuminated generated charge carrier to the electricity. Illuminated charge is optical to electricity. So here you can see this is a little bit different ideology than the normal solar cells, because in solar cells we use the sunlight mode, and we try to understand just collect the free charge carriers, are electrons and holes in both sides. But in this case, it's a little bit different because they inject the spin from magnetic material to this material, and there is some photoexcited carriers, and these photoexcited carriers has electrons which contain electrons, spin up and spin down, and they try to understand how these spins interact with each other, and it leads to convert the sunlight to electricity. So this was the first paper came out, but all the things happened at 2 Kelvin, which is too low. It's quite hard to realize in room temperature at that time. So later this guy from the University of Washington, one group, they've shown this 2D material system. This is based on chromium trihydrate that I said, which is very unstable material, and they are able to show the same thing. So if we have these two different layers, basically the spins each layer can interact with each other, and that can help to generate implement the protocol generate charge carrier in the system. But all these devices work at very low temperature, like less than 10 Kelvin. So our main motive is how we can improve this high temperature, because this material purity temperature is very low. That is one reason. But our materials, our functional materials is room temperature ferromagnetic properties. So we are basically focusing to understand the device efficiency, working principle, and the stability of these devices. So I will just give you a highlight because this is not finished work. So here what we are using our material, that's the magnetic materials, which is stabilized into graphene electrodes, and here you can see some device structures. So we are first trying to understand the spin or magnetic coupling in this system, in optical and the electronic, both sides. So here basically the PL, you can see the huge quenching. That means we have a huge drag of the electrons and holes in both sides. Otherwise we should not see this quenching of this PL. So here just a schematic diagram of how these electrons and holes can transfer from each side of the system. Now the important part, if we talk about the magnetic system for the spin photovoltaics. So we talk about magnetophotocourrent of the system. So this is basically a measure of zero magnetic field and a certain magnetic field divided by the zero magnetic field. This is actually the measure. So at a certain voltage, you might have a huge change in magnetic resistance. So this is one of the published paper in Nature last 2021. So we have also observed the similar in our system, which is around 40 millielectron volt, but it is much higher elevated temperature than this one. So here you can see our one devices where we have mounted before loading the sample. I will come to the next slide how we measure the system and stuff. So, and also we did some optics as well in this system. I am not going to show in details because this is not published yet. So yeah, here we did some the control device. This is basically based on the MOS2. It's a non-magnetic material, so you cannot see here any change with the magnetic field, especially the open circuit voltage in the system. So that means that our system is working well. Oh, I already discussed this. Okay, so I must talk about the system where we are measuring. This is basically the commercialized one, and here we have the part that we have developed in the system for our measurement. So this is actually the auto view, and it has a magnetic field, and it can go like 4.7 for few millikelvin in the system. So it has three parts basically. This is the laser detector part, the excitation source, and the detection part. And here is the optics head. Basically, we can control the system because it's a very tiny device, like few micron or 10 to 20 micrometer devices. And here is the electronic feed through, where we can connect our devices at the bottom of this chamber. So here you can see in the enlarged view. And here basically see this is a holder basically, sample holder. Here is a sample which is connected to the pins for the electronic measurement. And you see here is objective lenses. Basically the laser comes from here and fall on the sample. It's quite hard because it's a few tiny micrometer devices and the laser is 1 micrometer spot size, and it's quite challenging task to focus your laser beam in a particular location of your device. So yeah, maybe I'll come to the next slide for more details. So apart from that, we are working with this material for other applications, especially the magnetic, as I mentioned, magnetic tunneling junction, and also the spin thermoelectric properties of this material. Here one device that you can see. So we are also collaborating with different groups in the United States. So yeah, you can see some of them like Columbia University, North Carolina State University, and Auburn University. So yeah, apart from that, we are also working on quantum physics devices. I'd say this is a US Army project. We are working on the GPS system. So we are developing some graphene ring devices. I will just give you a highlight because this is an Army project and it's a bit more confidential. So we are developing some small devices to locate the position of any, let's say, any aircraft, vehicles, or the persons who are working in this field. Because navigation is very important and there is some certain limitation that I don't say here. So what we are exactly doing, we're fabricating very small tiny devices, thousands. These are one single devices, but these devices are like thousands of devices. We are connecting parallelly and we're trying to improve the efficiency in terms of the the accuracy of the GPS location system. So it's based on basically the Van der Pau or Arnold oscillation, quantum physics, so Landau oscillation. So this is some, let's say, demonstration of system. So yeah, so this system that I have been developed has last 2-3 years. So one of the Logan-Richard Raman with magnitude electro-optics measurement in the system, which can go 4.7 to 475,000, and also we have developed this low pressure chemical vapor deposition. And here you might see more in detail when you do the experiment. This is actually a sample holder that goes down here, and here is the magnet, and we are employing the magnet in particle predictions. So yeah, when we work in the laser lab, it looks like that. So yeah, last part I would say, like, we're working, as I said, like the space mission. People are focusing on lightweight machines which can just take less power, and also if it is heavy, then you need a lot of power to send it in the space, right? So this is actually recently that project we have started. Is a low mass for the low mass vehicle, the quantum Raman spectroscopy. Right now we are working on the spectroscopy based Raman spectroscopy, but we are able to replace this the spectroscopy with a single proton detection system, which is very small and compact devices. So that we already delivered that system. And right now we're working for material science applications of this single proton Raman spectroscopy that's quantum based. Also some medical applications as well. So I believe in summary, I believe I am able to give you some introduction about the functional two-dimensional materials and recent research of this two-dimensional material space. Not only that, quantum physics and quantum device application of these 2D magnets. And I'm sorry. I'm sorry, it's not working. So I would like to thank. This is actually academic page. So I would like to thank you, especially my PhD supervisor. My PhD started at the earliest, I would say, then my postdocs and current institutes, especially the Center for Quantum Science and Engineering and the material departments, and also all the people who are associated with this work. And with that, I would like to thank you everyone for listening. If you have any questions, you can ask me. Thank you.